screen. I'll leave it up there because you could also see it in Google Meet. And we're going to go through the problem. The problem, again, is on page 763, the example. So you might want to look at that page. Name of the problem is combination special, right? So we got to turn this music off because I don't understand a copyright issue or something. All right, so let me do this. All right, so here we are, right? We need to turn to, like I said, page 763. I got it open already over there. Okay. Okay, so what are we working on here? Well, let's start with the basics, right? We need two equations. And here's why. One is, of course, a series circuit, right? The other one is going to be a parallel circuit. So here's what we're looking at. We have the R for EQ lower, which is going to be R plus R. The EQ lower, if you're not understanding, because this turns into a parallel circuit here. You see how it's parallel? This is a branch, and this is a branch of splits. We have to combine them. So first, we have to combine R2 and R3. All right? To do that, we use our series equation from the past. So for resistors in series, when you're looking for R and Q, you use R, E, Q. In this case, they say lower, if you're reading it, is equal to, and that's the lower rung, those two resistors, R1 and R2. So that'll be, like I said, the R2 and R3. So that'll be R2 plus R3. Those are those two. Series is easy because you just add them up. You end up getting 2R here.
What's that say about REQ?
REQ lower. So if you look, Pearson, at page 763, I'm on step 1. You see how it says R subscript EQ lower? Okay? All right, moving on. Again, follow 763 so you know what I'm writing. Once we do that, these two resistors will combine as one resistor. Then all we have to do is figure out these two. So we get to consider REQ lower as basically R2 2 times R, because they're the same. Every resistor is 560 or 555 in the problem. Over here, this is for resistors. You got to use this equation we used yesterday in parallel. All right, you saw that it looks. It's a parallel circuit, and that's 1 over REQ, right? Which we played with yesterday. And these will come up on Thursday for your quiz. We got no class on Friday. We're going on a trip. So this is going to be basically, you're going to use what here? Well, keep in mind, you got R1, so it's going to be 1 over, this is both of them being combined, REQ, right? You got to do this first, then you can get to this part. So that's equal to, what do we say, 1 over, that's R1 there. Plus, we got this other resistor is now 2R, right? Because this basically becomes this. Since these are the same resistor values, you just say 2R. So that'll be 2R, or 2 times R, the same resistance. So now we're ready to set up our known and unknown values, and then of course solve for this amazing problem. So, known. What do we know? Are you talking to me or you're freestyling something? Okay. All right, so who would like to get some points? Who can tell me what's in this problem? What do we have?
E equals 14.7.
Thank you, sir. Electromotive force, or epsilon, that E. It's a Greek-looking E, is 14.7 volts. 5 points, Mr. Carson. How about anything else? We got 3 resistors, so you can easily tell me what they are.
You said we only see 5. I mean,
3 resistors in there. But I told you already, they all have the what? The same value. So what is this? Thank you. All the way down, right? So 555 ohms, 555 ohms, 555 ohms, or omega. I'm going to put a big R there because when you do this part, it's still 555, but it's going to be times 2. So R is just 555 omega. All right? R1, R2, R3, just so you know, they're all the same value. What about unknowns? What are we looking for here? Huh? Yeah, you got points for 3 of them though. It's just saying when we get to this step in the equation. So let's go through it, right? What is unknown here? What is unknown? If you look at the book, it'll tell you. Or you could look at the problem and it'll ask you. So in this circuit, Pearson takes electromotive forces, blah, blah, blah. You say, what? Current. We heard you say that all wrong. Current. Current, bruh. So I, very good, sir, is equal to question mark something that will be found in amps. All right, let's work this problem out so you can have time for your exit slip and your you do section. Okay, so let's break it down. We know that REQ lower, let's work it out. This is step A, solve for REQ, and this is lower, right? To do that, we use this equation, which is REQ lower is equal to R2 plus R3. Now, there's 2 ways to do it. I'm doing it this way because you can see virtually what's going on. You could have just went 2 times R. Either way is fine. All right, so let's plug in the values. You know, REQ, lower is equal to, what was our R1? I mean, R2. It's 555. They're all the same. You can say 555 omega plus 555 or 555 omega. Okay? So that means REQ lower branch is equal to what? Let's put it together. Just calculate it. In case you don't want to do it, think about it. 5, 10, carry 1, 5, what? 10, 11, carry 1. You know, so you do it that way, or if you don't feel comfortable, you just say 555, and that's 1,110 ohms. Okay? Almost through, because you got to use this somewhere else. The next step, of course, is you got to find the parallel combination. Huh? So you can't see the answer? Okay, so now we got this. Our next step, of course, is called step B. It is to find out what happened when it becomes a parallel circuit. Because we got rid of the series portion of the circuit. So now solve, right, for, it's like 1 over REQ now. This is for your parallel circuit branch. So to do that, you take this equation here, and that is simply 1 over REQ. We use our calculator button for that. And it's equal to 1 over R1, which is pretty much the same as R2 or R3, plus 1 over what we call our REQ lower. We're going to combine these two. Okay, and we know what REQ lower is since we just calculated, right? So let's continue on. I'm going to continue on over here with more room. That means your 1 over REQ, there's more to this than just what we're about to do. You got to flip this to get REQ by itself. So that's going to be equal to 1 over what was R1. Well, that was 555 omegas or ohms. Plus 1 over, what was our REQ lower for that series connection? It's 1,110 omega. And I'm going to use a calculator for this. And then we got a step after this before we're done, because that's 1 over REQ. It's not REQ, so that's a problem. So to do so, let's continue on. It's going to be just an iteration next. 1 over REQ, the total REQ of the circuit is going to be equal to, like I said, let's put the calculator in, use the fraction button, because if you don't use the fraction button, you got to do common denominators. I know people can't stand that. So we hit this button. Are you going to do it, Carson? For 10 points, if you got it. I'm going to press the fraction button, 1, press down, that's 555, press the arrow key over, plus fraction button, let's use another ratio, 1, come down, and it was 1,110. And what did you get? Okay. He's frowning. What happened? So that is the circuit we created a while ago. To what? 7?
Yeah.
Yes, sir. 10 points. All right. So again, for students that wasn't there, that's the circuit over there that we recreated, and it's going to snap together and make one series circuit. We're going to draw that at the end. All right. So let's go ahead and put that up there. It is, Mr. Carson calculated it with me, 0.0027, and this is not exactly what we need. So we got to do one more step to it. This is omega, but raised to the -1. So I want to get rid of this. So in order to do that, I want to get just REQ. What I'm going to do is, and I'm on step if you're confused. Where is it at? Yeah. I'm on step 2. All right? So when you do this, you just simply, like I said, you raise this to the -1. That's how you reverse this. Right? And you do the same thing to this section. Right? The inverse. And what happens is what? Well, when we rewrite it, we'll end up effectively with REQ is equal to. Where?
Top of R. I mean 1.
This is a -1 here. It's raised to -1, the whole fraction. So use caret or use superscript. All right, so let's plug it in. I'm going to take the same answer, and like I said, I'm going to raise it. I'm going to put the answer down, hit the caret, and then put -1. And I get 370 ohms, which is absolutely REQ. Okay? So that is... Yes, because they cancel each other out, so you can get this, right? Take your time with that. All right, we got one more step to go, and that's, of course, finding our current. We can find it using an old equation known as Ohms Law. So I'm going to turn this over this way a little bit so you can see what's happening. Ohms Law, if you don't remember, right, has 2 or 3 flavors. And we're going to talk about which one we use. So Ohms Law can be written as epsilon or EMF is equal to the current multiplied by the equivalent resistance, which we're going to use. But another derivative of it is, if you didn't notice, V is equal to, you have potential difference as opposed to electromotive force. You have voltage is equal to the current multiplied by just the basic resistance. Okay. So we're going to use this one here to find our current in the system. Reason being, we have REQ, we figured that out, and we're going to use it in conjunction with our electromotive force after we do some algebra on it.
370?
370, yes. So we're going to use it to find out what our I is here. So let's do the algebra right quick. And we're going to say, hey, last step, and remember, you're going to be using this REQ over here, right? So last step is really, let's say, step C right, is where you would figure out, solve, I should say, for I, which is your current. So let's get this started. I'm going to use, like I said, this equation here because I have electromotive force and I have V, and that's I. We're finding that REQ. All right. What do I do to separate these two to get I by itself? Anybody know? A little bit of algebra right there. Divide by what, sir? Yes, 5 points. Way to go. So let's rewrite the equation and do what he just said. Okay. You got the hang of that algebra. He said, hey, I'm going to divide by REQ because I want I by itself. So to do that, I'm going to say, hey, divide by REQ. Once you do to one side, you got to do to the other. Ooh, girl. And, oh, you're back. You better hurry up. And this recording will be available later on. So you probably will get the codes from him. And a simulation recording was made too. So cross these two out. Huh? And the new equation is I is equivalent to epsilon REQ. Okay? Final phase, remember we found REQ here, and we got voltage in the known section, so we just plug in the numbers and calculate the final answer. Someone will get 10 points if they know what they're doing. So I is equal to, let's finish it off, our voltage was 14.7 volts, right? Divided by our REQ, which we found to be 370 ohms, or mega. So I effectively is equal to what now? We'll take a look at this calculator, this wonderful calculator. You can just put a fraction in and punch in those numbers. So let's go ahead and take a look. And I won't say the answer. Let me see if somebody can get it for 10 points. So that's 14.7 up top. Say what, sir?
0.039.
You the man. 0.039 is an effective answer. And that's your amps. 0.039 amperes or amps. Effectively, what does that do to your circuit? You see the circuit over here is what we started with, Alika. It's a big circuit. Now all it's going to do is what? Well, think about it. We combined all these resistors, so now you have just this going on. You still got this bottom part with the battery, but now you only got one resistor, and this is pretty much your REQ. Yeah, see how it squeezed all those down? Mm-hmm. Say what, Carson?
I said you still going on?
No, I was just showing you what you did mathematically. Okay, you don't have to do this over here because you got this in simulation. But the reason you did this calculation is because this circuit, you squeezed all those resistors down into one resistor, is what I'm trying to show you. And technically, it'll be just one resistor there connected to a battery. It makes the circuit more efficient, and in terms of functionality with the current, you don't have to worry about things burning up as much. Okay, so take in all parts. Again, this recording will be available later on today. I did post the other videos from yesterday. If y'all want to review that, you can go back and finish something. So take advantage of it right now, all right? We have effectively 11 minutes of class left. I'm going to set a clock for about 9 minutes, I want to say. Give you a little time to finish up. It's the same as, yeah. Change the numbers, recalculate, Mr. Carson. You got a few errors you got to change numbers in, right? So let's put the exit slip on the screen for you. So y'all can look at it on your Google Meet version if you're trying to figure out what to do. Like I said, we'll try my best to get this video into the system in both videos. It'll be 2 separate videos. If you scroll up in your messages or if you go in your classroom and scroll down a little bit, you'll see the video of the demo I did with you in simulation and the calculations I did for yesterday's parallel problem. This one was important because it's series and parallel combined, all right? Definitely get the notes for this because Thursday there's a quiz on it, which is y'all last day. Now, let me here, stop this.